Welcome to the third lecture of mobile robotics. Today's topic is on nonlinear Kalman filtering. That's the continuation of the previous lecture on base filter and linear Kalman filtering. And today we will see two methods for nonlinear filtering. By the end of this lecture, hopefully you're convinced these are good ideas to solve some of the problems that we come across. But most importantly, you should be able to answer the question that why we need something like extended Kalman filter as opposed to the Kalman filter itself. If you're not convinced why and when you should use the nonlinear version, and what's the core question that leads to development of that nonlinear filter, you should ask it, right? We should reiterate why. I want you to be convinced when you walk outside of this, then there shouldn't be any confusion when you should go with extended Kalman filter, when you should go with the Kalman filter, okay? So we talked about the dynamic Bayes network as a graphical way to show the causal relationship between variables and how the state X evolves over time. We also pointed out that in a graphical modeling course, you learn these graphs are super useful because we can model conditional independence. In other words, if you write down the joint probability distribution of all of these variables, there are so many terms to deal with if you factorize it using the chain rule. But if you have this graph, it encodes the conditional independence, and the product of these basically factorized probabilities that we see here, it forms the joint distribution. So that's the motivation for a graphical modeling, and that can be a topic on its own. So we just used to motivate the structure of the problem here. So the shaded variables are known, Z is given. The arrow was showing that it is being at that particular location that causes the robot to, for example, take an image or a point cloud scan. And the motion command helps the robot to transition from one state to another. So we could write down the probability of xt given xt minus 1 and ut minus 1. Sorry, ut, right? So conceptually, what this tells us is that a probabilistic model that helps the state to transition from time step t minus 1 or k minus 1, we're talking about discrete time steps, to time step k using a known deterministic command, right? You signal, for example, move forward for a delta t of 0.1 seconds, right? The robot will move forward as much as it can, and then maybe you have a model to predict where the robot will be. But because there is no perfect actuator in the real world, and there are so many, for example, the carpet, or maybe there's a bump, right, as the robot is moving with wheels, it won't be perfectly at the place that your model will tell you. So necessarily, you will deal with some noise or a region for possible location that the robot can end up, and that motivates the probabilistic model for that. So the noise will capture that. It's supposed to capture that basically region that we hypothesize the robot will be. So that's the probabilistic motion model. For the measurement, I should write it here, we have a likelihood model that uses Markov property that it is shown in this graphical model, because when you condition a variable on the parent node or all the nodes that are pointing to that node, it becomes independent of all other nodes. That's the same thing as the Markov assumption. So that's the likelihood and sensor model. So in the state estimation problem, our goal is to estimate the posterior over the variable x given observations and control inputs, z and u. The specific way you attempt to estimate x or derive a probability distribution over the posterior leads to different methods. You can have Kalman filter, you can have particle filter, you can have Bayesian inference, or generally speaking, that can be classified under the topic of inference, right? The specific way you want to do inference is a little independent of this general notion of what is given, what we want, okay? We're talking about the filtering aspects of inference. That means we don't track the history. We only estimate at any time the state at the current time step, okay? So the Bayes filter, in the previous lecture, we went through the derivations of this. It leads to this prediction model and observation model. The prediction model showed up in the marginalization step where we can use the previous belief, which was the definition of posterior at time step t-1, to predict the posterior, the belief, at time step t. Then we could use the Bayes rule to use our likelihood and belief as prior to do a correction. The particular model that we used last time, it took the form of t f t-1 b times u plus some noise, right? This is a linear realization of this probabilistic model. So there is a deterministic part and there is a stochastic part. If you drop the noise, the model is deterministic because we assume the command u is deterministic. You can assume command is noisy as well, but you can decouple it into a new noise term and then name it again w, right? So that's okay. We can deal with that case as well. So previously, we were dealing with linear systems, and the likelihood model, the linear version of this was z equals h xt plus some noise, okay? The reason this is probabilistic or stochastic is because of the noise, not because of the model, right? The same model without noise is deterministic. Because whatever is the realization of x will give you 1z. Whereas if you have noise, the noise follows a distribution at every time it can have a different realization, okay?
I'm confused for the prediction step still why we have the belief term and the integral. Like I understand that the belief is like the prediction, so we want to use this probability of the next state given the previous state and the input. But I'm confused about belief of x t-1. Why is that there?
Why this term shows up here?
Yes, and also why is it in the integral?
Two questions. So you have two questions. One is why the belief xt-1 shows up here. The second one is why there is an integral. So the integral is, I answer the one that I can here first. If you have a probability distribution, marginal distribution of x, or maybe I use a notation that is similar to that. If you have joint distribution of xt and t minus 1, sorry, the marginal distribution of xt equals, according to the law of total law of probability marginalization rule, summing over or integrating over the joint distribution of xt and xt minus 1. Of course, it can be any other variable, but we're interested in a recursive. So we look into the joint distribution of xt and the previous step. So this is true, and you don't need any particular model. This just follows from the laws of probability. You can integrate out any variable. If you specifically want to evaluate this integral, of course, it can be hard. It depends what is the model for P. For example, if it's linear, if it's Gaussian, we can evaluate this integral exactly, which makes it very efficient. If it's more complicated, you might not be able to do that. Then you have to do it numerically. It can be more intensive computationally speaking. Now,
Hi, Professor. One more question. This is for the continuous situation, and what if it's discrete variable?
I'll answer that in a bit, okay? So just to finish this, you can also write this as, using the chain rule of probabilities, you can write this as conditional distribution of xt given xt minus 1 times p of xt minus 1. I'm dropping all the extra terms, u and previous observations, right? You could include all of those. Now you can see this term here as, again, I'm simplifying the notation so I can quickly make a point. This is your previous belief, right? This recursive form pops up here because we see the marginal distribution of x at time t as a joint that was the integration over the joint, right? And this is, of course, your transition model. So hopefully that answers both of them, right?
Yes, thank you.
Okay. It's a good practice. I encourage you to derive it one time for yourself, and maybe let us know in Piazza, and that can perhaps help to internalize it or memorize it. Now, another question was, why do you write integral? What if it's discrete? That's not a problem. You can change this to sum, okay? It is still true. It's just when it's continuous, we're talking about densities. Gaussian distributions are continuous densities. If you're working with probability mass functions, those are discrete. So we need to write the discrete time equivalent of, which is discrete equivalent of the probability rules, and those are using summation instead of the integral. Does that answer your question? Okay. So whenever you see an integral, you can think about it, I could write it as sum because that's for the discrete case. So part of the course is, as we move forward, we will explore more of these motion models and observation models for different examples and problems. But it is more convenient to talk about a class of problems and an algorithm that can be applied to a class of problems. If the class of motion models and observation models are linear with additive noise, then we can talk about the Kalman filter. Then that's an algorithm or filter that we can apply to a class of problems. that is scalable, because then as soon as that problem fits into that category, we know what's the method to use to solve it. So it's a matter of efficiency and organizing our methods for different problems. And of course, this is a part of your specific knowledge as an engineer. When you face a problem, you can decide what to use, and you're familiar with that tool. So again, this is a summary. We have a stream of observations and motion data or action data. We have a known model likelihood and a transition model. We want to estimate the state of the dynamical system, which is the posterior or belief over xt. And you could put it in an algorithm. The literal implementation of that, as we pointed out, is the Markov localization in that circular world that you're implementing. So today, we want to talk about a new class of problems. Now the model is no longer linear, which happens to be a lot of time for a lot of interesting problems we want to solve. So the process model can be, so instead of f, x, k, minus 1 plus b, u. By the way, this f and b, they can be time varying, but they're linear. There's no, it can be a linear time varying system. That's also allowed. You just have a different f and b matrix. Or I'm mixing up, should be f and g, or sometimes people use a and b, but it doesn't matter. So it's not like that. It's just whatever linear combination of x and u. And when I say linear, if it's linear, if y equals f of x, if it's a linear map, you can write it as this, right? Or in other words, alpha y1 plus beta y2 equals f of alpha x1 plus beta x2. This is a property of a linear map. If it's nonlinear, you're not going to have this structure carried over to the output, which makes it, in general, difficult to know what to expect. Okay? But depending where you are in the domain, the behavior of the nonlinear model can change as well, which makes it super challenging. It depends on your operating point. If the robot is moving fast, you might get a different behavior. If the robot is moving slow or turning, you might get a different behavior. Then you can expect different level of accuracies and performance from your algorithm based on your mode of operation. So the process model is nonlinear. The measurement model is also nonlinear. A nice case still is that when the noise is additive, okay? You have a deterministic nonlinear model with additive noise. Same for the measurement model. A more general case that also includes this additive noise is when the noise is also multiplicative. You cannot decouple the process plus some noise term. Maybe it's somehow mixed up into nonlinearities. For example, you have a log or cosine, and then somehow noise is mixed up here, right? It's not decoupled from the entire process. It's somewhere inside. But this, of course, includes the additive part as well, okay? So in this case, your nonlinear process is a function of two vectors. One is the state, one is the noise. It's like a multivariate function, but all of these can be vectors. They're not the scalars. So that's what we mean when we talk about nonlinearity. Is this process still Markov? You're nodding. Somebody raising hand?
I think maybe yes, because we don't have any past time states in the argument of the function h.
Partly true. You're saying yes because we only need the state from the previous time step. What about the noise distribution? Does it matter? What if the noise correlates everything with the origin, initial time?
Does the fact that there's only ek and not ek minus 1 or ek minus 2 say that you only need the correct times noise?
Okay, so you're relying on the notation, but the notation can be misleading because maybe this comes from a distribution that relates all of them. So it's a colored noise. That means it does have autocorrelation. Okay? So yes, because yes, that's true that we rely on the previous time step, k minus 1. But if you remember last time we said a process can be nonlinear. It's called Markov if it's excited by a white noise. So the noise needs to be zero mean white noise. That means it doesn't have any autocorrelation. Okay? Otherwise, because of the noise, you do track the history. As you move forward, everything is getting correlated. Okay?
So the same thing holds in the linear case.
Yes, that's true for linear case as well. Right. So the Markovian part is not about linearity or nonlinearity. But it is no longer linear Gaussian or Gauss-Markov because you start with a Gaussian, but it is nonlinear. It doesn't, unless you have a special way to exactly have the transformed distribution on the other side, right? And it happens to be Gaussian, it won't, you cannot say that that's Gauss-Markov process. So that structure is lost in a sense. But it's still memoryless and Markov because of the assumption we put on the noise. Okay? So one central question that's really the main question in this lecture. I have a nonlinear map, nonlinear function, and I want to send a probability distribution from its domain to its range. How can I do that? I know how to do this, let's say for Gaussian distribution, and if the model is an affine model or linear model. Why? Because that's the problem you're dealing with assignments and all the questions on Piazza, because basically the Gaussian distribution is completely described by its first two moments. The covariance is the central moment. But using the characteristic functions of that probability distribution, you can prove that through an affine map, you can still exactly have the first two moments. And that describes your Gaussian. So it suffices to propagate exactly mean and covariance. If you can do that, then you have the exact propagation. Now, the problem is when the map is nonlinear, you go ahead and you want to take the mean and maybe write down the definition of the covariance, and then you expand the terms, you end up with nonlinearities that you're not sure what to do, okay? That's what I literally mean. You write it down, you try to do it, and you get stuck. You don't know what to do. You cannot derive a closed form formula. So that's the problem, okay? Not a problem for us. This is an important problem in physics too. Okay? Maybe in particle physics, for example, you track a distributions, maybe you have nonlinear partial differential equations, and you want to propagate it over time. You're not able to do it exactly. What's the solution? So does this make sense? There's a distribution here, maybe it's Gaussian. There is a nonlinear function. F is a mapping from some domain to some range. This nonlinearity can perhaps makes this distribution to be like this, right? Or maybe make it like this. Whatever it might be. Again, based on different region of domain, this nonlinear function, we don't talk about one nonlinear model, anything that you can imagine. So then the output is not something that we can guess necessarily. So that's the problem. We're looking for ideas to rectify this problem. Simple ideas that we can still keep the track of this recursive estimation. There are some ideas, linearize it. That's true. 99% of the time in engineering, we linearize everything, okay? It's not specific to this class, this topic, this area of work. We love to linearize everything in engineering. Basically, when you're out of idea, linearize it, okay? That's your default state. You can still get paid if you do that. Nobody will complain. So just say it was nonlinear, I linearize it around the operating point. It sounds good, and you get paid. That's the extended Kalman filter. Okay? Sampling from the domain. Any sort of approximation method. That's true. Basically, you can come up with any method that can solve this particular problem. Then you can build a filter around it, okay? It's not limited to these three, but these three covers a really wide range of ideas that we have in literature. There are a couple of more newer ideas out of the scope of this lecture, but I might mention it in the end. So 3 key ideas related to us. Linearize it. How do we linearize? Well, that's the Taylor's theorem. If you have an analytic function, meaning that your function is differentiable for infinite number of times. If a function has all its derivative for an infinite number of times, you can write down the Taylor expansion. That means write down your function around some point that you want, not necessarily 0, it can be any point, using its derivatives up to some order. Now, when you go higher order, of course, it becomes nonlinear. But if you only keep the first part, that's the linear part, the first derivative. Okay? That's the linearization.
So the function should be monotonically decreasing for that, or can be increasing as well?
Well, the only condition on the function is that it needs to be analytic. That means its derivatives must exist. So it must be differentiable, not in the modern sense of deep learning. There was a tweet that it used to be that differentiability means that left and right derivatives exist. You get the same answer. Now it means that there hasn't been a Python package implemented for it to give you the derivative. So I don't mean that, I mean it in the classical calculus sense. You write down the definition of the derivative, the left and right limits give you the same answer, right? This function at 0 is not, right, differentiable because the slope as you reach to this point 0 changes suddenly. Depends on what direction you're arriving, right? They disagree, and that's a problem. A differentiable function, no matter what direction you approach that point, you get the same answer for the slope. That's a nice property. That's the smoothness property, basically. So we want the functions to be continuous and smooth, roughly no sharp edges, right? We don't want it to be like this, right? Discontinuity. Then, so under some regularity conditions and nice settings, you can linearize. The second idea that has been extremely successful is called on-center transform. The name does not mean anything. It's not meant to. Don't think about it. It doesn't mean anything. It's just a random name. It is deterministic sampling. You generate a set of samples based on a deterministic rule. It's not random. And then you use those samples to approximate a distribution, a Gaussian distribution, on the outside, the range of the function. The third idea, which is known under the Monte Carlo methods, is based on random sampling. Using computers, now we can generate pseudo-random numbers. So you can generate many random numbers or samples in the domain of the function, and then send them through the function to the range, the output, and then you have a lot of samples in the range. And then basically you have built the histogram in the outside, right? So it's a way of generating histogram in the domain and then getting another histogram in the range. So I have maybe a Gaussian initially, right? Send it through this function. Maybe the functions give you something like this, right? And next time, it's not Gaussian anymore. You're dealing with this one, right? And you just keep evolving this through this nonlinearity each time.
Referencing what you were saying, does the Monte Carlo method ever suffer from the fact that, like you said, that computers, unless they're referencing something, can't generate purely random images?
The question is there any problem that the computers cannot generate exactly random numbers? You need to pick a seed and then they're pseudo-random numbers. No, we ignore that. We just assume that they're random. Well, because we get good results in practice, then we don't look back. Right? If you ignore something and then your method doesn't work, obviously you need to go back and see if that's the root of the problem. But because we get satisfactory results in practice, we ignore that.
When we're, I guess, mapping in this case, when we sample an X and then run it through the model to produce Y, this would take more of like an observational work, right? So I guess like after you have a model in Y, and then are you assuming that your sampling is just like wide enough to the point where when you get like a new sample, and so instead of now like running it through the model, you have to just like map it like almost like a test set type of thing?
So your question is, we're assuming that this histogram, this set of samples, it is covering the actual distribution, right? We have enough samples, and that's true. That's a problem. We're going to talk about it soon in particle filtering. But that's an assumption that, or at least it's a problem in practice, and we need to make sure we have enough sample to cover the space. And you might not know how in practice, okay? So these three ideas for solving this problem, this challenge, leads to different methods. When you use linearizations, that goes under the name of extended Kalman filter. So we come up with an idea to solve this problem, and then we go back and basically fix the original Kalman filter to get a new algorithm, right?
Excuse me, Professor. So what do you mean by how to map belief distribution through a nonlinear function? Because I think for extended Kalman filter is linear function. Mm-hmm. And the last two methods are sampling methods, and they can be nonlinear according to given maybe the motion model. So the first method should be linear function. I'm not sure.
So your question is why we have this problem here, right? Let me break down your questions. Let's focus on the first one. You're saying that if we linearize, then why that's a problem, right?
Yeah.
Well, the problem disappears after we linearize. Before that, that's a problem,
Okay.
right? You forgot where we were. First, we had no idea. We had a nonlinear problem. Then we linearized. Then, as we will see soon, the problem will disappear. And then we have to do this linearization again and again, right? So you're right in the sense that we're going to deal with linear models in the end, but that's the remedy. That's not how it was.
So when we are saying we want to map, are we simply looking for how to compute integrals efficiently?
How to compute?
Integrals, because there is an integral term in belief. So are we looking at, because all these methods can be used to compute integrals in a more efficient.
In a sense, yes. So the question is, when we talk about propagations of a belief through a map, are we talking about integration? Yes, that's a really good point, and that's how I could start. The reason I don't start from there because it can get more confusing. But generally, the problem is that you have a nonlinear function, and then you have a nonlinear, or you have a distribution, whatever it is. What you want to do, you want to calculate the moments of this map, right? The first moment, according to that distribution, is the integral of this. The second moment, you need to raise it to the power. The third moment. Now, if the distribution needs 4 or 5 moments to characterize it, right? You need to take a lot of integrals. There's a good chance. So the landscape of the integrals you can calculate exactly are much bigger, much smaller than the landscape of the integrals that you cannot evaluate exactly, okay? So this is the core problem. Typically, you want to get expected value or moments of nonlinear map with respect to a distribution. If you can't do that, then you can build some algorithms, okay? So in the broader range of these ideas, if you look at the inference or a lot of machine learning methods, that's what they want to do, okay? And Monte Carlo methods is a way to approximate these integrals. So yes, a lot of problem arises from integration. We want to integrate, we don't know how to do it. Numerical integration is at the core of a lot of these ideas. Now the integral, it disappears when it's linear and Gaussian because we have an exact result. You don't see the integrals.
So can we understand like this? So for sampling method, there's no integral in our during sampling and resampling process.
There is, so the question is, there's no integral in the sampling methods. There is, I'll point out, where you can think about it as integration. Basically, when you have a weighted sum, that's an integral. I'll point out later. So the linearization method. We're going to talk about the extended Kalman filter first. Extended because, well, it's the extension of the linear Kalman filter to nonlinear models. Suppose we have a function that maps from Rn to Rm. Not the same number of input and output necessarily, but of course, if it's your transition model maps xk minus 1 to xk, so the input-output dimensions are the same, okay? But generally, from Rn to Rm, if you write down the Taylor expansion and only keep the linear terms, so don't keep the higher order terms, right? You have higher order terms, drop them. What you have is the function evaluated at the operating point, let's say A, plus basically this is your Jacobian, right? The Jacobian or the derivative of your function with respect to the variable you want evaluated at that point. So it's no longer variable. You evaluate the Jacobian, it's a matrix in general. If it's a single variable, of course, it's just a scalar. If it maps a vector to a scalar, you have gradient, right? If it maps from vector to vector, then it's a Jacobian. We'll talk more about it in optimization again, but you've seen these ideas most likely before. Now, you rearrange this by keeping the variable x, right? And just keep everything that is not variable. Ultimately, this will give you some vector, x0, right? x0 is not variable. Your Jacobian evaluation is f, and x is the variable. Now, this is an affine. When you linearize, so you can always do that. If the function, again, is analytic, you get affine, and we know how to propagate a Gaussian distribution through an affine map. So the problem is solved by this method. Just a reminder, if it's an affine map and you have a Gaussian, you have this formula. Now, however, to evaluate the mean, you don't have to use the linearized version. You could just use the function. But for the covariance, you have no other choice. So really the reason we linearize it is for the covariance. It's not for the mean. Because for the mean, you can just evaluate the function. That's easy to do. All right, so let's go back to the Kalman filter algorithm. So we don't have to go through the derivations because we had an algorithm for the linear case. We're reducing the nonlinear case with the linearization idea to the linear case. So we're going to modify that algorithm. And then we're going to talk about what do we lose. It cannot be that we approximate and then we don't lose anything. There must be some consequences here. So we linearize the process around the current mean. For the belief. When you think about in general for multiplicative noise, you also need to linearize your process with respect to noise, because that's another vector that is input. Okay? If it's additive, of course, you get the identity map. That's a nice case, right? So if you have fx plus w, the partial derivative of this with respect to w is identity because, well, this part doesn't depend on w, right? But if it's inside, so when you see it like this, there's no need to panic. It's just one more Jacobian to calculate. Because, well, it's just another input, right? In other words, the Taylor expansion of the function f of x and y, you need to evaluate it for both of them. If you have 10 variables, keep going, right? So whatever number of inputs you have, you need to consider all of them. Which the Jacobian is already doing that because x is a vector. You could write it for x1, x2, x3, and so on. But we want to distinguish the state from noise, so that's why we are separating like this. For the sensor model, do the same thing. Notice the operating point is changed. We do it after prediction. Potentially, you want to linearize your observation model as at the predicted state. That's supposed to be a little better, right? Pick the best linearization point you have at any time. It is possible to come up with other choices as well, but these are obvious choices you can come up with. Same thing for the observation model. You can linearize it with respect to the noise if the noise is multiplicative. So let's see how we can modify the algorithm. First step, so the input is the mean and covariance of the belief at time step k minus 1. We need the action and the measurement as the input. Use the nonlinear process model to predict the mean. To propagate the covariance, use the linearized model. Again, WK can be identity if noise is additive, right? So you're just going to see Q. Use the predicted mean in line 3 to predict the measurement and calculate the innovation. If you remember previously, this was h times mu k, right? Now we're using a nonlinear map. Calculate the innovation covariance, S. Again, V can be identity if noise is additive. Kalman gain. Kalman gain is the cross covariance of your predicted state and the measurement times inverse of the innovation covariance. Think about it for a moment. If the noise covariance of your sensor is very large, that means your sensor is what? Accurate or precise?
Local variance is precise.
The inverse covariance is called precision matrix for the same reason, right? So it's, if the covariance is large, that means your sensor is imprecise. Because you can have a very good sensor, you have a sensor that is very accurate, right? But as you repeat this, it has a lot of noise around that accurate measurements that you can get. That means if you take 1,000 measurements and then take the sample mean, it gives you the correct answer. It's not, let's say it's not biased, right? However, if it's biased and not accurate, because each time that bias will appear in some way, if you take the sample mean, that won't be a good value to work with. So that's why it's very important to compensate the bias of the sensor, offline or online. If the sensor is imprecise, that means in the limit you can get correct answers from that sensor. Which you will see, I think, in your homework too. You have an example of that. But because there's a lot of uncertainty, when you get one measurement, you're not sure where it is, but somewhere within that covariance ellipsoid. So the amount of information that you add each time will be reduced. Inverse of covariance is the precision matrix or the information matrix. Large covariance, small inverse, right? Small amount of information entering the filter. So this term will be small. Sorry, this term will be big, S inverse will be small, right? Is that correct? So small, big noise, small innovation information. Small innovation information, small filter gain. The filter will not trust that measurement too much to correct your predicted state suddenly by big amount. It will do it a little by little. You will need to collect a lot of observations to gradually see that the filter is hopefully converging to the correct value. If your sensor is unbiased, you don't face any other problem. So you can make sense of these terms. They are very intuitive. Despite their unfriendly look, you can give a lot of meaning to them. So if you have a very good sensor, possibly expensive, maybe with 1 or 2 observations, you can quickly converge. So the linear update rule, updating the covariances, they're all the same. We don't change anything. Except H is, again, linearized model. So that will give us the extended Kalman filter. If you can implement a linear Kalman filter, and you have a way to get the Jacobian of the map, maybe by hand, maybe you use a symbolic package in MATLAB, Python, Julia. You don't have to do it by hand. Or maybe you use automatic differentiation and get it numerically. There are a lot of packages that can do that for you. Somehow you will get these Jacobians, then you should be able to modify that linear Kalman filter to have an extended Kalman filter. Okay? So it's no harder than the previous case, except you need to handle these derivatives. Okay? Analytic formulas for the derivatives, of course, will make it faster. If you have a closed form evaluations of these Jacobians, if the model is simple, it's very beneficial for real-time applications. If it's too complicated, and still you can get good performance, maybe you can try to use automatic differentiation. And by the way, automatic differentiation in Julia is just one line. You import the package and define your functions, and then you get it. It's not something that you might be worried about it, right? There are very nice libraries at this point to handle automatic differentiation. I'm actually not sure if MATLAB has that, but Python definitely supports that. Julia supports it as well. There are libraries for C++ as well. Okay. So do you have any questions so far?
So we linearize only one time for FK, right?
Good question. The question is, do we linearize one time forever? No. You linearize, maybe you linearize to get the formula if it's analytical or closed form, but every time you start running this loop, you have to evaluate your Jacobians, because your linearization point will change. Mu k minus 1, next time that you enter the algorithm, is the previous mu k. So that's a very good point. Reevaluate these terms that you see above here each time. So you have my example codes for this problem, and also a class of EKF that will basically take these analytical Jacobians from you, and it will reevaluate it each time inside. Take a look how I implemented that class. It should clarify this question. So let's revisit the target tracking example. There's a 2D target. We know the on-ship position, fixed at the origin. This time we make it a little more realistic. The sensor is giving you a range and bearing. The angle relative to, let's say, forward looking, and then range. You do have physical sensors like radar to get this sort of measurements. Or camera. A camera will give you just the angle, right? You don't have a depth, but maybe if it's a depth camera, you get depth and angle. So the state is, again, 2D position of the target in the plane. So basically, we're tracking x, y in a 2D plane, okay? We need a geometric relationship between the state and the quantity we actually measure. The quantity we measure, z, you can think about it as range and angle. The range is obviously the Euclidean distance. This unfriendly notation I'm using, I could use it like this, but it means basically I mean xk1, xk2, okay? So take the Euclidean distance of your state. This will give you r, right, the range. And the angle with respect to the y-axis will be that arctangent 2. Okay, so now we have our measurement model that relates the state to predict the measurement. It is clearly nonlinear because of the squared variables, the square root, arctangent 2. The prediction is the same. We do not have a model for how the target is moving. So my transition model basically is xk equals xk minus 1. That's it. F is the identity, G is 0. There is a noise, but when you evaluate the mean, the noise is 0 mean, okay? That's why you get this transition model. So in this particular example, the transition model is actually linear. You do not need to change that part. But the observation part is nonlinear. Overall, leads to an extended Kalman filter still, because part of it is nonlinear. You can evaluate the Jacobian of the measurement model. It's not very difficult. You will get this matrix. Again, you can use software. You don't have to do it by hand if you're lazy. Then it's the same old Kalman filter. You just update H every time based on where you are. So we're using range and bearing. The filter can actually track a 2D Cartesian coordinates of this target. This is a more realistic problem for tracking a single target. So look at the example code in MATLAB or Python. Let me know if you have any questions on Piazza. Let's summarize. So this filter is still very efficient, just like linear Kalman filter. You can run it in polynomial time in terms of your measurement and state dimensionality. Kalman filter typically runs at the quadratic rate because matrix multiplication is, for square matrices, is cubic, as bad as matrix inversion. Now, efficient libraries can bring it down to 2.3 or something, right? But nominal computational complexity at worst is cubic. Because matrices that we use, this H and K, are rectangular. They're not actually square matrices. Going by the bigger dimension, you will get quadratic cost. So Kalman filter can run at a quadratic cost. So if you have 1 million variables in your state vector, this will not scale. But if you have 100, sure, that will be fine, probably. Not optimal. Why? Previously, the linear Kalman filter was optimal. We said it's the best you get, even if the noise is not Gaussian. And if, in fact, the noise is Gaussian, that's the optimal filter for linear systems. Why? The theoretical result is lost. It's no longer optimal. Because it's nonlinear, we linearized. We made an approximation. As a result of that approximation, you cannot claim that we maintain the theoretical results.
Is there a
error is between the nonlinear system and your linear approximation?
The question is there a way to characterize maybe some bounds or some relationship between the error and the filter performance? That's always good to do if you're approximating. I'm afraid not something that I'm aware of it, probably because you need to talk about the particular class of nonlinear models. If you're claiming for every possible nonlinear models, it's probably not possible to derive a bound. In the invariant Kalman filtering, we will see that there are some models that are linear exponential. In exponential coordinates, they become linear. So then we get some of the lost properties back. That is a big motivation why to use that coordinate system. So in general, no, it's not optimal, or people tell you, my algorithm is suboptimal. That's just a nice way to say it's not optimal. So when you hear suboptimal, it's converted is not optimal. Unless they give you a lower bound, right? My algorithm is suboptimal and lower bounded by this error, probability of error.
Last time we stated, and today, we stated that the linear Kalman filter is optimal. But did we show that in lecture at some point?
Do we show that? We definitely didn't show it in the lecture. That goes back to the proof of the filter, right? In the sense of minimum mean square error estimator, that's the best filter we get for the class of systems that are, for the class of estimators that are first unbiased, right? Second, they're linear. So they get best linear unbiased estimator, blue. That follows from a theorem. It's called Gauss-Markov theorem, which applies to least squares as well. And because Kalman filter with linear least squares are the same, that's one way to show it. We did not go through that. If you're interested, that's a good conversation to have, maybe on Piazza or office hours. But to clarify, the question is, how can we show that Kalman filter is optimal linear filter? Then we need to look into proofs for the class of estimators that this filter tries to compete with. But the topic is blue, best linear unbiased estimator. An unbiased estimator in expectation, let's say, will converge to some to the true value, right? If it's not, it converges to something plus something else. It is obviously biased, right? So unbiased means this is 0. There are biased estimators that can perform better. So this filter can diverge. That's one problem. If your nonlinearities are severe at the current operating point, depending on the behavior of your models, the filter can potentially diverge. However, in practice, for a lot of problems, this works really well, despite violating all the theoretical results. So that is why it's it's widely adopted and used, because of good performance in practice. But again, there are robustness concerns, depending on the particular problem you solve. So one of them is, for example, a SLAM. If you do EKF SLAM with a lot of landmarks, that's a concern because if you do wrong data association to assign a detected landmark to the wrong previously seen landmark, then the filter can diverge. You're injecting outliers, wrong information to the estimator. And EKF is very brittle with respect to that because you linearize, it's a filter, you move on. You never look back to correct that, right? You just recursively linearize and move forward in time, and you never go back to correct previous approximations. That's the reason. There is no chance to go back and correct it. So when the outlier enters the filter, it can lead to divergence. More on that in SLAM. Yeah, because your function can be maybe like this, right? It's not too bad. But if it's like this, your slope changes widely as you move a little bit, right? Basically, think about it this way. For a small change in the input, what is the delta, the change in the output? If it's also small, that's good, okay? If it's delta in the input is small, you perturb the function a little bit, the output changes a lot. That's concerning. In control theory, that's the topic of stability, okay? Robustness means that these changes are for the bounded input. The delta in the input, if it's bounded, the output is also bounded. It won't go to infinity. Again, in control theory, you call it robustness. You are sure that your system won't blow up for some regions that you make a delta change in the input and then suddenly the system breaks down, right? That's robustness. We are talking about more related to the stability. Because if the delta in the output is large, it will not, the linear model is unable to capture the behavior of your model. It's not sufficient, so that then you can expect results won't be satisfactory, right? Does that answer your question?
Couldn't it just be a linear model with a high slope, then a small change in input, a large change in output if you have a linear model with a high slope?
Linear model with large slope and small change in the input will give you potentially large variation, right?
Yeah.
When the slope is becoming vertical.
Right. So why is that a problem? Like you said that's a characterization of high nonlinearity.
Oh, why that causes a problem?
Yeah.
Okay, so the reason is because the slope here maybe is some line like this, right? You move a little bit, right? And this is not a good. Now suddenly maybe the line is like this, right? The delta in the x direction is small, but the delta, the change in the slope in the y direction is very large.
So if you went down the function, you could just get off the actual nonlinear function.
Sorry, can you repeat it?
No, I think I understand now what I'm saying. If you can diverge from the nonlinear function if you're going towards from a region with a high slope to a region with a small slope.
Yeah. And then the bigger concern is that, well, this is one time. We'll keep doing it in a loop, right? You do it a few times, these approximation errors will get accumulated quickly. That eventually might lead to divergence. Now, I'm not saying maybe one time, the little error, maybe you get lucky, right? The accumulation of these nonlinearities and approximations can lead to divergence. Okay. So I'm not a control theorist. I'm not bothering you with delta epsilon stuff. I'm keeping it more practical. But this is also a dual problem of control. This is estimation, but still you can think about those stability and continuity conditions for your estimator. Okay, next topic is uncentered transform. Second idea. Well, the idea is like this. Compute a set of samples. We call these samples sigma points. Why? Because we use sigma for covariance. These are points generated from the sigma. Then people decided to call it sigma points. That's my guess. Never verified it. Well, it doesn't matter. Some samples, these are deterministic. We'll see why. Then each sample comes with a weight. And then we transform these points through a nonlinear map, such as G. Once we have our samples in the range of this nonlinear map, we approximate the Gaussian distribution using weighted sample mean and weighted sample covariance formulas. Basically, that's the steps we will follow. Now, you could come up with many ways to choose these sigma points. This sounds like a very reasonable way because covariance is PSD, and if it's not degenerate, you can factorize it using a Cholesky factorization. The Cholesky factorization will give you an upper triangular matrix L, sorry, a lower triangular matrix L, right? All the terms above the diagonal are zeros. And L transpose obviously will be upper triangular. Then we generate, and then we also scale this with some factor. We call it L prime. So N these are just numbers, right? N is the number of sigma points, and kappa is just the tunable scalar. So the first sigma point is your mean. Mean sounds like an important point to consider. Then we generate 2n samples like this. Around the mean, we generate a bunch of vectors. Then we add and subtract them to the mean. How do we do that? Using this L, the scaled version of L prime, Li, this is L1, L2, Li. This is Ln, or L prime, if this is L prime. These Li's are the columns of this scaled Cholesky factor, okay? In the first note I gave you, you will see how we can convert a sphere into an ellipse. From points that are on a unit circle, you can use this Cholesky factor to transform them. This is equivalent of a rotation and a scaling, geometrically speaking, to an ellipse from a circle. That is why when we use the columns, we get different dimensions in space to move the mean. This is purely motivated by the geometry of how this covariance is scaling your standard, let's say, circle or sphere into an ellipsoid. And then we have a bunch of weights. I'll talk about it in a minute. We evaluate the sample mean using these weights. Related to your question on integral, basically this is the expected value of g of x with respect to some probability, right? If you have some samples, you can approximate this using a weighted sum. There are many methods for numerical approximation. If your distribution is Gaussian, and you want to do this for any nonlinear map, Gauss-Hermite, for example, is a good algorithm. Monte Carlo is another one. In any way, you can approximate this using some weights and evaluations of your function. This is how numerically you can approximate. Now the question is, what are the weights, right? In different algorithms for numerical integration, you have different ways of finding these weights. So it is a form of integration or calculating expected value. For the covariance, now we can evaluate a weighted sample covariance for our 2n plus 1, because I starts from 0, right? Up to 2n, we have 2n plus 1 samples. The first one was mean. We get n sigma points by adding the columns of Cholesky factor, right? Covariance is n by n. You have n columns. Add each column to the mean, you get n sigma points. Also subtract them, you get another n sigma points. So you get the covariance as well. The cleanest way that I like is in the state estimation book, how to get these weights. There are older references. It can be more complicated. You can have multiple parameters, but this is very clean. You have one parameter to set, and you can always start with 2. Right? Super convenient. So the first weight is different from all other weights. But notice that this adds up to 1. Right? So it's normalized. Sum of all weights is 1. So only the first weight is different for the mean. More on this topic you can read here in the textbook. Okay, so that's how you do it. So you get another Gaussian distribution propagated through your function. It is deterministic because these samples follow from rules here. It is not random. If you repeat this process for the same covariance and mean, you get the same answer, right? As you repeat it, it won't change the solution. So it is deterministic. Whereas later we will see in the Monte Carlo, your samples are random. If you repeat that, you don't get the same specific values for each term. But the hope is if you have, because of the law of large numbers, probably you get similar, more or less similar results overall. So that's why it's deterministic. One tricky part. If the noise is additive, you only need to, so if the noise is like this, or if the noise is additive, you can just do this on center transform for the nonlinear part. And then you add the covariance of noise later to that weighted, basically, sample covariance that you calculated. Because obviously W is added to the range of this function, right? So it's already in the range. However, if the noise is multiplicative for any reason, the solution will be a little more complicated. What you need to do, you need to stack them into a bigger vector, and your n is no longer the dimensionality of the state. It's the dimensionality of the state plus noise. So if it's 10 and 10, you get 20, right? So you need to generate more sigma points because now you're augmenting the state with noise. Now you don't have to literally do this, but you need to think about it that way as a distribution. So you have x, k, wk distributed according to some stacked mean, which is mu k and 0, right? Your noise is 0 mean in this context. It's a white noise. And then create a block diagonal covariance, okay? So generate your sigma points using this augmented system. Then you send both the noise samples and state samples to the range and then calculate the sample mean and sample covariance. So that's the trick when the noise is multiplicative. However, because the algorithm will look very ugly, the algorithm on my slide is for the additive noise, okay? When you implement, you will come across this case as well. Example. Now we have the range and, so it's just the coordinates, not the range and bearing example. So this is a mapping from polar coordinates to the Cartesian coordinates. It's a simple example. So you have, for a point, right, you have rotation, angle, and then you have x, y. So x is r cosine of theta, y is r times sine of theta. We're working with a specific mean and covariance, right? We want, and this is my nonlinear, basically, map. And this r and theta distributed according to mean and covariance that you see here. So I want to propagate this distribution from one coordinate system to another coordinate system. However, there is an uncertainty that I need to map. Otherwise, you would just evaluate this function. So in the polar coordinates, r and theta, if we were just stretch and flatten the angle, we look at it as an axis here. The distribution looks like this. You have a mean, and these are sigma points, right? So you can see that with a particular parameter, kappa 2, which is good for Gaussian distributions, the sigma point, what they're doing geometrically, they're really getting the corners of this ellipsoid, which makes sense. We don't want to just do the mean. Select a bunch of points around this ellipsoid, send this shape through the nonlinear map, see what happens the other side. and then use that shape to approximate the Gaussian. Previously, in the extended Kalman filter, we were just working with the mean. So this intuitively, you can expect this method to be at least slightly better. Sounds like a better idea. So when you map it to the Cartesian coordinates, it is interesting that the weighted sample mean is not aligned with the mean that you actually evaluate your function. In the EKF, the mean is just the evaluation of the nonlinear model, which is this point here. However, the uncentered transform tells you don't work with that, work with this linearization point, right? So this point is basically when you evaluate this function using this mean, right? Does that make sense? Plug in 1.5 and pi over 6 to this r and theta function. It will give you 1x and y. This will be this blue point here. Okay? Now go through the uncentered transform process to evaluate this mean. This guy, right? When you evaluate this weighted sample mean from the uncentered transform, it will give you another point just here. Now, this is not too bad. This is a nice example. So they're very close. They can't be far. So you get different results as a result of this process of deterministic sampling. And the way these points around the covariance are distributed, you can also see. And this ellipsoid is a 95% confidence region.
So in AI, why we just calculate the new mean by just put those mu into the function, but here we use the function.
So the question is, in EKF, why we just evaluate the mean by plugging it into the function? My question would be, what else do you recommend us to do? What's the alternative?
So in EKF, we calculate with the estimate as a linear function.
Mm-hmm.
So we just estimate as a linear function.
So you're saying instead of the nonlinear function, use the linearized version. So that's even worse. You're replacing the exact nonlinear process model using an approximation. At the very least, for the mean, we could use the exact process model, right? So the part that you're thinking that, well, maybe that's not the best idea, right? That's true, but then that will be another algorithm. EKF as is, that's how we call it, right? That's how we understand it. It is true that with different ideas, we can improve it. That's not necessarily the best way of doing it. So the alternative ideas will lead to different algorithms, such as the uncentered transform, right? But when you talk about EKF with somebody, that's what we mean. Okay?
Excuse me, Professor. So what's the difference between the red circle in the right red circle and the blue point? What's the difference between the 2 points?
These two?
Yeah.
So blue is here. Blue is x equals r cosine of theta, which is 1.5 times cosines of pi over 6. Y equals r times sine of theta will give you pi over 6. That will give you the blue point, even though I wrote it with red, right? The other one, the result of the uncentered transform, you need to generate sigma points, Cholesky factor, right? using the Cholesky factor and then calculate the weighted sample mean. That will give you this point here.
This point is by directly sampling from the...
Well, you need to, I think you're confused about the algorithms maybe. Let's say there's a black box method that will do it for you. It will give you this point, right? My point is that it's not the same thing as you calculate this. This part is clear, right? There is a magic box that will give you this point.
This magic is what?
Is on-center transform. It is not the same as evaluating this. That's my point. Now you might want to know what's inside the magic box. That's the on-center transform. It could be other methods too.
The on-center transform standard method is to, the first sigma point is just the
mean, right. You got it right. The first one is this point, but also you have all the other points. And then take the weighted average of all these points with their corresponding weights, right? That will give you this red circle. Yeah, maybe this is a better way to visualize, writing the weights. I think this is a better way to show it.
So you said that the dot, the black dot, which you can now label W0, is not from the uncenter transform, but from just taking the mean and putting it through the nonlinear function. Is that true?
Yes, every black dot here is a sigma point, including the mean itself, that has gone through the nonlinear map.
Oh, I see.
Then we have to approximate this Gaussian using the sample mean and sample covariance. But because they don't have uniform weights, we use the weighted sample mean and weighted sample covariance. Does that make sense?
I see. And so the red ellipse now is generated from which samples? On the right-hand side, we've got this ellipse. And it's a little bit confusing because we showed that we can't move a Gaussian through a nonlinear function. And so where does the red ellipse come from?
So the question is, we talked about the fact that we cannot propagate a Gaussian exactly through a nonlinear map. And that's true, this is not exact. We're just approximating a Gaussian in the xy domain instead of r and theta. As we will see moving forward, which is I'm just saying that 95% confidence ellipse, so that means if you draw 100 samples, 95 of them will be inside this ellipse, right? Now, if you make distribution a little complicated in the sense that the orientation, the angle will cause, maybe this distribution becomes narrow like this. Now, when you propagate many random samples, which is really the Monte Carlo way of doing it, you see this shape here, right? Banana shape. This is the true distribution. At least the true distribution have something to do with this shape. We are approximating using the Gaussian. In fact, it's not like it at all. That was just the nice example, the first one, right? So it could be that it works well. It could be that it's completely off in the sense of the mass is covering a much larger space than the actual distribution. Yeah?
And then you said that the small red circle point is the mean of the left side plot sent through the uncentered transform.
Yeah, the circle red in the middle is the mean that you get out of uncentered transform, which is the weighted average of all these black dots, sigma points.
Okay.
Yeah?
Is there any chance we adding or increasing the sigma point will make the Gaussian fit more well upon this kind of banana shape?
The question is there any chance that we increase the number of sigma points and then we can model some complicated shapes like this? No, because how are you going to model this using an ellipse? This is just a different shape. We'll see that in the exponential coordinates we can model this exactly. Right? This is still Gaussian in the exponential coordinates. There is a choice of coordinates that will make it Gaussian, but in general, the answer is no. We're just doing the best we can with the Gaussian, right? You're a little disappointed, but this was a really good idea. And it still is. So it's very efficient. So it's not going to solve everything, but at least it's better than just linearizing using the mean. Okay? Progress is incremental. We cannot solve everything at once.
So the point here is that if the covariance matrix is 2 by 2, we can only sample 2 multiplied by 2 plus 1 points.
You can get more. You can come up with different ideas. That's just the standard way that was published. People documented that. Maybe if you like to come up with a better idea, you can do research and publish that as well.
And the second
then we will use it.
There is only Gaussian distribution we are modeling. We cannot model other. We cannot model other.
Well, because we're in the context of Kalman filtering, we want to estimate mean and covariance, right? It is a nonlinear Kalman filtering. I'm not talking about any inference. In the context of Kalman filtering, we want to track mean and covariance. So that will give us a Gaussian distribution, right? So very quickly, but these are really good questions. Let's continue them, right? Let's continue the conversation on Piazza. Great questions. So the filter is a slightly different because now we need to work with sigma points. But go through it. But the core of it is that basically you apply uncertain transform one time for prediction, right? To send your previous belief through the process model. And then you can generate a new set of sigma points using predicted mean and covariance. Use that to predict the measurement using the nonlinear measurement model. Using these new sigma points, calculate innovations using this predicted measurement, innovation, and cross covariance. So because we're not working with analytical derivative of the measurement model, H, we need to also calculate the cross covariance. The cross covariance is that term that you see, right? In the probabilistic derivations, there are cross terms. This is the cross covariance of the measurement and the state. But this comes for free. If you look at the uncentered transform class and the UKF class that I implemented, you already have it. This comes for free. It's just between your state and the measurements. Again, the noise is additive to keep the algorithm clean. Calculate the filter gain, update rule, and covariance update. Covariance update, it looks different, but it's equivalent of previous equations. You can just expand it and see that you can get the other equations from it. Now, why? So you can implement this for the same target tracking example. So the same problem that you apply EKF, you can also apply UKF. It's because you have the models, they're nonlinear. You get to choose which one, right? Now, for simple problems, the performance will be very similar. Check the sample code. This filter is also very efficient. It's typically within the same computational complexity class as EKF, but it is slightly slower because you generate more samples Just instead of just mean, you're working with more number of points. It is a slightly slower, but not so much. By a constant factor, maybe. You get better linearization. On top of that, it's derivative free. This filter is derivative free. You do not need to calculate derivatives. It's nice. If you implement it as a generic, basically, method code, you can apply to a lot of problems without calculating the derivative. So that's nice. Same true for this filter too. It's not optimal because of that polar coordinates already is giving it away. Imagine more complicated examples. What can happen?
So if UKF is more precise and easier to implement than EKF, then when would it be better to, or when would you prefer EKF over UKF?
The question is, if UKF potentially is better than EKF, why would somebody with in the right mind use EKF? Not in exact words. Well, EKF came first. You need to look at it in a historical context, first of all. It wasn't that UKF was sitting around and somebody said, well, I have a new idea, let's do EKF. No. It was Kalman filter, then extended Kalman filter, then unscented Kalman filter. So enough, I don't know, 5, 10 years maybe. Difference. So that's why. Another thing is that EKF is potentially faster. Maybe you do have really good models and you can derive the Jacobians. And it can be potentially faster. But generally, yes. If you want to make sure this will work better, maybe you can go with UKF. Again, in the invariant Kalman filter, using the exponential coordinates, you see that we can get constant Jacobians. Well, then it doesn't make sense to use UKF. Maybe it does. Maybe you can get a slightly better performance. But if your Jacobians after linearization in certain coordinates transformation becomes linear, that a lot looks like linear Kalman filter, right? So that motivates us still to use that. So that's a class of error state EKF. Instead of linearizing the model itself directly, calculate the error dynamics and then linearize the error, because covariance is basically centralized moment, right? You may as well centralize it around the true state. And then when you do that, for certain problems, the error dynamics becomes independent of your state. That's a little confusing now. But there is a magical relationship that sometimes you get, and that will be the topic of future lectures. Then still EKF is a really good choice because also it works really well on the robot. There's a UKF version of that as well. I have not implemented that. But you should be able to do it if you want to after we talk about it. So that EKF that I told you, we can run it at, let's say, 2 kilohertz. 2,000 times in 1 second, this loop will repeat on a, let's say, legged robot. That's a lot of iterations, right? And the state includes position, orientation, velocity, gyroscope biases, accelerometer biases, foot position. So 3, 3, 3, 9, 15, 18, at least 18 or 21 variables. So, but I think the short answer is the timing, right? So a lot of time you get similar results, better approximation for nonlinear models. No Jacobian needed, slightly slower. Sampling becomes inefficient as your state dimension will grow. EKF does not have that problem, right? So you can read more on the nonlinear Kalman filtering, but what I gave you is basically a digest of both books and other literatures. So that's it for today. Next time we will talk about particle filtering.